In question number 3, we're going to start with a given recursive equation. And again, you can tell that the hallmark of a recursive equation is this n plus 1 notation. That actually might be just a quick little note that you'll want to make to yourself, maybe just something to keep in mind. And although I'm folding up the bottom of my paper just to make myself a bit of scratch space, you may want to consider recording this on some sort of note sheet that you can keep for long-term notes, like with things that kind of carry you through the whole chapter, because this is probably an important distinction to make in terms of vocabulary. A recursive equation is always going to use the t of n plus 1 notation, where an explicit equation is going to use the traditional t of n notation. So you might want to, again, make that distinction clear, just so that way you kind of know the difference. Recursive is going to use t of n plus 1, and explicit uses t of n. Some textbooks do actually vary a little bit their notation. I've seen, for example, some textbooks use a sub n plus 1 and a sub n as the notation for a sequence, and if they don't use the t of n notation. We can certainly be flexible if notations vary a bit, but notice again, even in this different notation, n plus 1 is still a recursive idea, where just n on its own is explicit. And you might want to think of it in those terms if you know what the words recursive or explicit mean in more colloquial language. An explicit value or an explicit term is something that gets directly to the point. They don't sugarcoat it. Something explicit is generally very direct and very clear. So t of n, we're talking about n. The explicit equation tells us explicitly what's happening to n. It's a very direct equation. A recursive equation refers to the idea that recursion is a repeated series of actions or a repetition. So n plus 1 kind of tells you that I'm looking forward, I'm thinking about what's next. Recursion usually means take what you have and get the next thing. So in order to find a recursive equation, this t of n plus 1 notation suggests I'm going to find what's next. N is now, but n plus 1 is what's coming next. So I'm going to focus on that. And that really is the difference between the two of them. You'll see them both come up. They both have different applications in the real world that we'll eventually talk about. But for now, just kind of knowing that explicit is what's happening now, and recursive is what's happening next might be a good differentiation to keep in mind. Explicit is what's happening right now with the term that you have, n, and recursive is what's happening next, n plus 1, the term after the one you're dealing with. So going back then to question number 3, this one says t of n plus 1, so what's happening next is that we're going to take our current term, t of n, and we're going to add 6. So I like to kind of translate my equations just so I can get a sense of what they're saying. This equation says to get to the next term, take your current term and add 6. So that makes sense. And that sounds familiar. In letter A, where it says, where have we seen this equation before? That was the exact same recursive equation that we ourselves wrote as the answer to number 1, letter D. So I'm not going to fully write a sentence here, but I'm going to make a reminder to myself. I have seen that equation before, which means I'm hopefully continuing the problem that I've already done. This equation was the one that I wrote when I was doing my little table for the pattern where I was adding 6. So negative 8 plus 6, negative 2 plus 6, 4 plus 6, 10 plus 6, and I was doing all those plus 6s. So yeah, that's where that equation came from, and that makes total sense. To get to the next term, take the current one and add 6. To get to the next term, take the current one and add 6. That definitely makes sense. But in letter B, notice this other guy is claiming that he has a sequence that can also be represented by this recursive equation. Let's look closely at his equation for a second. His table of values, if I want to translate it into a table, says that his first term is 0, his second term is 6, his third term is 12, his fourth term is 18, his fifth term is 24, And I'm looking at this saying, okay, well, if I wanted to get the next term, the sixth term, I would have to extend the pattern. The pattern does look like it's adding by 6, so I would have to take the current t of n value, which is 24, add 6 to it, which is 30. That does look like it's making the pattern continue, and that looks like his equation really is correct. T of n plus 6 does work. Now, that hopefully brings to mind a very curious question. How is it possible that one equation could have yielded two completely different sequences? That doesn't seem like the math that we've always known and loved. The math that we always know and love is like one equation for every one answer. That ambiguity doesn't happen. If I gave you an equation and said, here, write me a table of values, I wouldn't expect that every single one of you watching this video right now would be working with completely different numbers. And yet here, we gave Dan this equation. He wrote these numbers perfectly acceptably. And yet we gave the person who wrote number 1 the equation, and they wrote a totally different series of numbers. And those numbers don't even have anything in common. I mean, yeah, they're all adding by 6, but none of the actual table values seem to even repeat themselves. We have completely different values in these tables. So that does beg to mind, how is that possible? Take a second to chew on that for a moment. How is it possible that the same equation could generate two different sequences? And should that be the case? Just think on that idea for about 30 seconds. I'm not going to stop the video. I'm just going to make a very awkward long silence that you can fast forward through at some point if you feel like you need to. But again, take about 30 seconds and think on that idea. Take a few more seconds to think. All right. Now, the reason why I wanted you to think on this idea is so you could really resolve for yourself the idea that these equations are just not clear enough. Remember the definition of the word explicit? Explicit is something that is very direct and very clear. Recursive equations lack that clarity. Recursive equations just say add 6. What they don't say is where to start. If I just told you to start adding 6, but I didn't tell you where to start and kind of let you pick whatever you wanted, you could probably come up with tons of different sequences. And I guarantee that anybody watching this video probably would think of different things. Here's kind of a quick little thought experiment just to prove to yourself how crucial this idea really is of being clear. Let me give you another equation I'm just making up that you're not going to see anywhere on this paper. It'll be t of n times 2. There's the pattern. T of n times 2. That's what I want to see a sequence in. I'm going to ask you to take a few seconds, maybe find some scratch space, make a little table, let's say first through 5th terms. Make up some sequence for me that has that pattern. T of n times 2. Take about, again, 30 seconds, or if needed, pause the video. Take as much time as you want to think about your sequence. Pick any numbers that you want to, but here's the challenge. I want you to pick the numbers that I'm going to pick. All I'm telling you is t of n times 2. That's all I'm telling you. So again, you're going to take about 30 seconds, and you're going to try to come up with the same numbers as I am in my table. 30 seconds, go. Okay, take a few more seconds. Okay, so here are my numbers. I chose 17, 34, 68, 136, 272. Were you right? Maybe. I mean, it's certainly possible that you chose these numbers, but I'll bet it's possible that you didn't. I'll bet it's possible that you didn't know where to start, so you just randomly picked some numbers. And I'll bet for some of us thinking about where to start, 17 was kind of a random choice. But how were you supposed to know that that's where I was starting? I didn't tell you that I wanted to start with 17. I didn't tell you that I was going to do that. So if you feel tricked, like, oh my gosh, how was I ever going to get that right? That's super unfair. You've just unlocked the biggest loophole of a recursive definition, is that a recursive definition can't just be the single equation of t of n plus 1, because it's just not enough info. The only way that we can do this is if I give you a recursive equation and tell you where to start. So let's try this again. Let's do another little thought experiment, but this time I'm going to give you more info. This time it might not feel like I'm trying to trick you so much. T of n plus 1 equals, and again I'm just going to make up something. Let's try T of n divided by 3. Let's say T of n divided by 3. But this time I'll tell you where to start. I'll tell you that T of, I'll give you the first term. The first term is going to be 12. I'll give you that right off the bat. Now, see if you can make a little table. Now see if you can do the first 5 terms with the fact that the first term is 12. I'm giving you that kind of as a bonus. And the equation, that T of n plus 1 is going to be T of n divided by 3. Take another 30 seconds. See if you can generate the table now. All right, so here are the answers that I know I came up with. 12 divided by 3 was 4, divided by 3 is 4 thirds, divided by 3 is 4 ninths, divided by 3 is 4 27ths. Now, of course, if you wrote decimals, that's fine. 1.333, and then 0.444, and then 0.148. If you did those as decimals, that's completely fine. But I'll bet this time we have the same table. I'll bet this time, even though the numbers were messy, we got the same thing. And you know why? It's because I gave you a start. I told you where to start. I didn't just make you start randomly dividing any old number by 3. I told you to start by taking 12 divided by 3, and then we got something to happen. So, in essence, this conversation has really been an attempt to answer question letter C back on your packet page. On question number 3, letter C, where it says, what additional information besides the T of n plus 1 equation is needed? We need to have a starting point. We need to have something that kind of like anchors us, so to speak, so that we know where we're supposed to start counting from. Because the recursive equation is going to do its job. The recursive equation is going to tell us what to do next. We just need to know where to start. So, a true recursive definition is actually going to have 2 parts to it. The equation itself and a starting value. This full definition is going to be what you can expect to see for a full recursive definition. Seeing both the starting term and the actual equation itself is kind of like a package deal. You cannot do any recursive problems without having a starting point. And it could be any starting point. I didn't actually have to tell you 12. I could have given you that the second term was 4, and you still could have gotten the same numbers in the table. I could have even given you that the 0 term was 36, and you still could have gotten the numbers in the table. So it doesn't matter which term I give you. I just have to give you somewhere to kind of anchor yourself so that you can continue the pattern and get all the numbers in either direction once you know where to sort of firmly set yourself. So now that you've kind of seen how recursive equations can look, take some time to really chew on question number 4. Because in question number 4, they're giving us recursive definitions and asking us if that recursive definition accurately describes the sequence. So if you're kind of confused by the structure here, think of both of those parts under the series of numbers. So the t of 1 equals and the t of n plus 1 equals as the full recursive definition. Because now you're being asked, does that work? Does that suit that list of numbers? So the easiest thing to do, in my opinion, is to go back and think in a tabular fashion again. So I'll do letter A just as an example. This one's telling me that the first term is 22. That's what t of 1 equals 22 means. First term is 22. And this is telling me to get to the next term, I'm going to take my current t of n term and add 11. So you'll notice I like to write my translation there. So to get to the next term, I'm going to take my current term and add 11. So I got the first term from the given part of the definition. Now let's see if the equation can help me get the second term. The second term, the next one, is the current term, add 11. So 22 plus 11 is 33. Okay, great. Then to get to the next term after that, I take the current one, 33, and add 11. Okay, check. Then to get to the next one, I take the current one, that's 44, and add 11. Okay, check. Now I'm going to go back and look, compared to what I see that they gave me originally. First term was 22, second term was 33, next term was 44, fourth term was 55, looks correct. It looks like that the first, second, third, and fourth terms that they gave me matches the first, second, third term that the equation generated. So I would say this one is true. And the explanation can simply be the table of values. That would be fine. If something is false, it's going to ask you to try to tweak the definition and fix it so that it does actually accurately correspond. So your goal is basically to make the table, put a little asterisk there, match the sequence. The table and the sequence should match. If they already do, it's true. If they don't, then fix the definition, fix the yellow part to make sure that you can force that match to occur. Take some time to try it, and just like always, check the answer key as you go. I didn't write anything in the answer key spots in the explain or fix, so I'm going to kind of leave that up to you because there are actually several different ways that you can fix a recursive definition to make it work. And I'm going to ask you to just kind of troubleshoot, but at least you can check which ones are true and which ones are false. That'll give you something to go on. Between now and the time you start the next video, work on question number 4. And then we'll do a couple more examples together at the bottom so that you can finish the rest of the page in the next video.